Greetings. Thank you for joining the talk. My name is Pedro Brito. I'm a professor at the Pontifical Catholic University of Minas Gerais, and this work is the result of a collaboration between Mendes, our university, the Federal University of Minas Gerais, UFMG, and the Senai Cimatec Institute in Salvador, Bahia. The paper is entitled Corrosion Resistance of Cold-Drawn ZK60A Magnesium Alloys as a Function of Strain Hardening. And this work has been presented at the 26th International Congress of Mechanical Engineering, Coelho. Introduction. So magnesium is the lightest metal used currently for structural applications, even when compared to other lightweight metals such as aluminum. The advantages of magnesium include an elevated strength to weight ratio, good damping properties, good castability, and good machinability. Disadvantages include an elevated chemical reactivity, low mechanical strength at high temperatures, and a low formability due to its HCP crystal structure. The forming of magnesium alloys may introduce preferred crystallographic orientations, texture, that may cause modifications of mechanical properties and also corrosion resistance. Based on these premises, the objectives of this work were to design and manufacture tools for drawing of a ZK60A magnesium alloy circular bar, then to evaluate the evolution of mechanical properties as a function of drawing reduction, to evaluate the influence of drawing reduction on the crystallographic texture of these alloys, and finally to evaluate the influence of drawing reduction on the corrosion resistance of the ZK60A alloy. The material which was used is a magnesium zinc zirconium alloy, which was received in the T5 condition, which is an aging heat treatment. The composition of this alloy is given in the slide: 6% zinc and 1% zirconium. And drawing passes were performed starting from an initial diameter of 25 millimeters and reducing to 24, 23, 22, 21, which corresponds to 7.8, 15.4, 22.6 and 29.4% cold work, respectively. All operations were performed at room temperature. After each drawing step, samples were evaluated concerning their mechanical strength by tensile testing, and also crystallographic texture analysis by X-ray diffraction were performed. These were carried out in a laboratory copper K-alpha radiation source. The reflections which were analyzed were the 100, 002, 101, 102, and 110 reflections. Porphyry data for analysis were obtained in the 25 to 65 degree in the tilt direction, and from 0 to 360 degrees in the azimuthal direction. And the individual diffraction spectra were acquired with a 0.1 resolution and 10 seconds exposure time. The corrosion behavior of the materials was analyzed in selected conditions, which were the as received T5 condition, the 22.6 and the 29.4 cold worked samples. All tests were performed in a 0.6 sodium chloride solution containing naturally dissolved oxygen, and a conventional free electrode setup was used with platinum wire counter electrode, silver chloride reference, and the sample itself. And in each case, the following techniques were employed. So, open circuit potential stabilization for 1 hour, followed by electrochemical impedance spectroscopy and potentiodynamic polarization. So, the results: mechanical strength behaved according to expected. As we increase drawing reduction, hardness and strength go up while ductility goes down. The data is summarized in the second figure of this slide, which shows that after approximately 20% of reduction, the loss of ductility and the increase in mechanical strength is more or less stable. Concerning the evolution of crystallographic texture, What is shown here are experimental pull figures in the T5 and 7.8% cold work condition. We can see here the main difference is that before cold work, before drawing, there is no particular or no strong texture component. After cold drawing, there is not a significant increase in the maximum texture strength, but we see a definite component in that the 100 plane becomes parallel to the sample surface. By increasing the level of cold work to 22.6%, the texture strength remains approximately the same, but just before, but in the final step, so when we achieve 29.4% reduction, the texture strength becomes significantly higher, and we go from 4.7 multiples of random distribution to 31.9, and the same component in all cases. This is remarkable because we noticed in the experiments that any attempts to perform additional reductions resulted in fracture of the sample inside the drawn die. So the 21 millimeter was the smallest diameter we could obtain via cold drawing. The data shown before in the pull figure analysis is summarized here. The texture data is consistent with a situation in which the 0001 basal plane of the magnesium structure is kept parallel to the flow lines inside the drawn die. As a consequence of this, we see that the prismatic plane will be parallel to the sample surface, and this is quite seen. This is neatly seen in the inverse pull figure of the 29.4% cold work sample, where we have the 01-10 plane strong component parallel to the sample surface, which does not happen in the as received condition. Moving on to the corrosion behavior, the samples which were selected for analysis were the T5 as received, the 22.4% cold work, and the 29.4% cold work. The reason for this was because for the as received sample we had no significant texture components and low texture strength. For the 22.4% cold work we had strain hardening and a weak texture component, and for the 29.4% cold work we have more or less the same level of strain hardening concerning the tensile results, and the same texture component in the previous sample, but with a much higher texture strength. What we see here is the OCP results showing that samples more or less stabilize after 1 hour exposure to the electrolyte, and the Nyquist plots of the impedance results, which show a slightly larger capacitive arc for the as received sample, which indicates a larger value of the polarization resistance, so a lower corrosion rate is expected for the T5 condition. The polarization diagrams did not reveal any significant difference between the samples. Similar values for the corrosion potential and the current density. And what can be said is that we have a slightly lower corrosion rate for the as received sample, since it has the lowest value of corrosion current density. But the differences are small. A small summary of the results. So the cold drawing process led to a small reduction in corrosion resistance, but no significant difference were observed among the different reductions. A possible reason for this behavior is that the different reductions had approximately the same strain hardening levels and varying levels of texture. However, the texture which was introduced by drawing was such that the prismatic 01-10 planes remained parallel to the sample surface, which are planes of average density, so they don't increase or decrease the average reactivity by themselves. However, the strain hardening process, which was observed, does increase reactivity, and that's why we have a larger difference between the T5 as received and the following cold drawn samples. We would like to acknowledge financing from CAPIS, finance code 001, and from Bookminas by the FIP project, and thank you all for your attention.